We are discussing multidimensional unconstrained optimization, and in last session we were talking about steepest descent method. We have seen the theory of steepest descent method, and we have also performed an exercise in an actual computer using steepest descent method. Now we want to talk about Newton's method. We have learned Newton's method in one dimension. We want to extend that method to multidimensional case. Newton methods is very fast and it gives a sort of a benchmark for all gradient descent type methods. However, Newton methods also has the problem, as it was there in one dimensional, it doesn't always converge. We'll not go very deep into the theory of Newton methods. We have already discussed that multiple times. So we'll see that how to extend it from one to n dimension, and then we'll solve a problem in this lecture. Recall our discussion on one-dimensional Newton-Raphson method. We were trying to minimize this function fx, and we started with an initial guess x0 over here. Then we are moving toward x1. With this algorithm, x1 is x0 plus h0 d0. d0 we have assumed negative of f prime, because this f prime gives us the direction left side or right side in one-dimensional case. It's super easy. So we are going against the derivative, which in multidimensional case becomes the gradient. Then to find the step size h, we were hoping that in one step we'll minimize the function. So in next step at x equals x1, f prime will be 0. Expanding this in Taylor series, we calculated the h0 to be 1 by f double prime x0. And then it gives us the algorithm x1 is equal to x0 minus f prime by f double prime at x0. So in general, we can write that in k plus 1th iteration value of x equals xk, that is kth iteration value of x minus f prime by f double prime at x equals xk. Now we want to extend this one-dimensional technique to multi-dimension. In multi-dimension, our x is a vector, and so is the descent direction hd. So following the same argument as it was in one-dimensional case, the multi-dimensional case will give us this xk plus 1. This is the same xk plus 1, but now it is a vector, is equal to xk, same xk, plus now it is a vector. This f prime divided by f double prime now becomes Hessian, and Hessian is a matrix, so we don't divide by the matrix, we take the inverse of that matrix. F prime now becomes gradient here. So this is our algorithm, and I'll not go any deeper into that how this algorithm is produced. You can try that yourself following the arguments in 1D case. Just like in one-dimensional technique, it may not converge, but when it does converge, they converge very rapidly. And sometimes to improve convergence, we use this Armiger condition to modify it. In Armiger condition, we use an h here artificially, artificial step size, and we modify it. So the Armiger condition, if we take, it will go like this. It will take an h, which is an artificial h. We will start with the initial guess h equals 1. This is exactly like steepest descent method. But in steepest descent method, we were trying to find h. Here in Newton's method, there is no h. We have, this is the step size multiplied by descent direction is this. But we are bringing an h to reduce this change in one iteration. Change in one iteration is this fxk plus 1 minus fxk. We are reducing that to stabilize the algorithm. Sometimes it helps in Newton's method for cases where there will be difficulty in convergence. This kind of reducing the h artificially may bring the convergence. The idea of Armiger condition is same as what we did in steepest descent method. We start with an initial guess of h, and then we see that if this condition is satisfied. If it is satisfied, it is fine. If it is not, then we will reduce h multiplying with a tau, and the usual value of tau is 0.5. So we half this, we bring this h to 0.5, then 0.25, etc., etc. We continue this process until this Armiger condition, that is this condition, is satisfied. So when we are taking h equals 1, that is actually the default Newton's method. When it is coming h to be less than 1 after we apply armature condition, then it is slightly modified Newton's method. Therefore, once the armature condition is satisfied, finally we get this our algorithm. This is the typical Newton's method with h equals 1, but now I have here is an h, so I am just being slightly conservative. Then what's Newton method will give me. So let's now go to our old problem that we were solving. We are trying to minimize this x square plus 2y square minus 2xy minus twice x. We have solved it using various techniques, but now we want to solve it using Newton's method, means this particular algorithm. We are keeping an h and we will play around with this h. We'll see what happens. Here the gradient is del f del x del f del y transpose of that, and we have found it several times that it will be 2x minus 2y minus 2, 4y minus 2x. Then the Hessian will be all the double derivatives. So if we take the double derivative of x with respect to x, that is del f del x, I take one more derivative over it with respect to x. So I get 2. If I take one more derivative of this with respect to y, I get negative 2. That is coming as this cross derivative. This is also the same cross derivative. Then del 2f del y2 will come from here, and that will give us 4. So now I can take the inverse of this Hessian matrix, and the inverse for 2 by 2 matrix is super easy. I have to divide it by determinant, and I switch these diagonal elements. Off diagonal elements, I change their sign. The determinant I can calculate very easily from here. So this is 4 into 2, 8 plus 4, that is 12. So this is 1 by 12, 4, 2, 2, 2. And now this del 2f inverse multiplied by del f, that means del 2f inverse is 1 by 12, 4, 2, 2, 2 multiplied by this gradient. I can do this multiplication for simplicity, and now I have calculated this change, that is del 2f inverse multiplied by del f. This is the change that the Newton's method is asking for in every iteration, and then we can bring this h additionally to be slightly more conservative. Analytical solution of this problem that we already know, just to remember that it will be negative 2, the minimum value, and minimum value happen at x equals 2, y equals 1. So roughly at this point it will hit its minimum. So now let us see, taking a computer program actually, how it will look like when we implement it in actual computer program. So here is my computer program of Newton's method. I have a line search here which is imposing the armature condition, but let's not bother about it now. Let us first see the default Newton's program. And here I have set an epsilon of 10 raised to minus 6, and my step size is default. This is 1. When step size is 1, this gives the default Newton's method. So my step size is 1, and then I have an initial guess of x that was minus 1, 1. I am using that guess for quite some time. Then what I do is that I have these two lambda functions. First lambda function is of course the objective function itself, and the second lambda function is an array, that is the correction, that is del 2f inverse del f Hessian's inverse multiplied by gradient. That correction I am bringing here, that will give me the descent direction. With a step size of 1, if I take this xk plus 1, then add this descent direction from kth iteration to it, I get the k plus 1th iteration value of x. So what I do here is that I start from this initial guess, and then with this step size 1, I come here within this for loop. I take this x, which will be x minus this step size into descent. Step size is 1. Descent is calculated from this lambda function here, that is my descent direction. And this b is, once again, this is the norm of this descent. When this is small, no descent is necessary. That means basically zero gradient has reached, and it will stop there. This is at this epsilon, that is my stopping criteria. If b, that is the norm of this descent, when it is less than epsilon, I'll break the loop and I'll go out of the loop. Then I have this objective function minimum value, and where the minimum value is number of iteration, I'm writing this. Below there I'm plotting the results just like I was plotting in steepest descent case. So now let us just run the program and see what happens. You can see that I was actually writing here all the iterations. So you can see that from very beginning it quickly goes down and it holds there. It comes to 1.94 and 1 for a long time, and it holds its position there. After 35 iteration, it is giving me the value of -2, that is the value of the function, and it is giving me the location 1.99 etc. 1. So you can see that this is same as analytical solution, which was -2 minimum, and 2 and 1 was the minimum location. So here you see that when I have this plot, the plot is very different from steepest descent. Steepest descent, you see a zigzag line here, but now there is no zigzag. It is just coming straight away toward the minimum. That is what Newton's method does. Initially it targets the minimum and it starts moving in that direction, because that is what the theory of Newton methods. The theory is that we'll try to finish our job in one iteration, and you can see that that is what it does. It has taken a target and directly rushing toward that. The subsequent iteration will be smaller depending on the epsilon, our convergence criteria, but you can see the efficacy of Newton's method. It takes very few iteration and it immediately goes toward the minimum point. Now we can work on it and impose the Armizo condition. If we put the Armizo condition, then I'll calculate the step size from this line search. Line search, what we are using is exactly the same as we were using before. Only thing that now this step size and gradient, this part is slightly different here, but it is basically the same thing. Now I have enabled this line, and this line, if I run my code now, the code, you can see that what it is doing, it did not change anything basically. It is giving exactly the same value. Iteration is same. The plot is same. So basically that Armizo condition is not doing anything here, because in Armizo condition we start from this h equals 1 and then we reduce it, but it looks like that for h equals 1 the condition is satisfied. Therefore it is still h equals 1. It looks that way, and it is giving us exactly the same results, exactly the same number of iterations. So now let us summarize that we have seen the theory as well as application of multidimensional Newton's method. From this method, because sometimes there are problems in convergence, there is a family of methods that we call quasi-Newton method. They have been developed. One such thing we are talking about is that imposing Armizo condition. Similar corrections on Newton methods are available. We work so much with Newton's method because this method is blazing fast as compared to many other methods, including steepest descent. For your exercise, you use Newton methods. You can use the program that I have shown and find the value of √2 from optimization of appropriate function. Thank you. That's all for this lecture, and I'll see you in next class.